Welcome to the ENME 351 video lecture series. This is part one of a three-part installment on Fourier transforms. In this lesson, we'll take an introductory look at the Fourier transform. A Fourier series permitted us to represent a periodic signal based on the frequency content of that signal. The question now is, well, what if we have an aperiodic signal? What if the period of the signal never repeats? So one way to think about this is that any signal is periodic if we let the period, if we let our capital T approach infinity. And there are obvious consequences of this. If I let t go to infinity, if I let my period go to infinity, then the spacing on my amplitude and phase spectrum plots, well, that's going to go to zero. And my amplitude spectrum plot, or what we commonly refer to as capital X of f as opposed to little x of t, those are now going to be continuous functions of frequency. If you recall the Fourier series, that was giving us discrete functions of frequency. Now, however, I have a continuous function of frequency as I allow this capital T, as I allow this period to approach infinity. To give you an idea of an aperiodic signal, this is me speaking into the microphone in my laptop, and I'm actually yelling very enthusiastically, "Let's go Terps!" And we can start to see some interesting effects here. You can start to see some of the quantization that has been imposed on this signal. And if I were to zoom in, you'd start to see some of the sampling as well. In fact, this was sampled at 8 kilohertz. But the idea here is that this is an aperiodic signal. It's a signal that's not repeating with time. So if I'm interested in understanding the frequency content of the signal, effectively the frequency content of my voice, I need to take a Fourier transform of this signal. There really won't be much value in looking at a Fourier series here. Let's quickly remind ourselves of how we defined a Fourier series. And we'll use this in contrast to how we'll define the Fourier transform. Recall then that Fourier said any periodic signal could be described by a constant term, in this case our A naught, plus an infinite sum of sine and cosine. So here we have our an, our coefficient for our cosine contributions, and our b sub n. Those are the coefficients describing the contributions of the sine signals, the sine components. And what was important was this fundamental frequency, omega naught, okay, in this case 2 pi over capital T, 2 pi over the period. And so the intent here is to sum multiples of this, integer multiples of this omega naught, all the way up from n equals 1, the fundamental frequency, all the way up to an infinite frequency, where n equals infinity. We defined our coefficients in this manner. A naught was our DC offset. You recall it was the mean of the signal. For a sub n, we were multiplying the signal, y of t, by the cosine of the integer multiple of the fundamental frequency. So for a given a sub n, we were using n times that fundamental frequency, n times omega naught. And similarly for our b sub n term, we're now multiplying our signal by sine of n, the integer multiple of omega naught. And you recall each integral, we're taking the limits from minus capital T over 2 to positive capital T over 2. And for a naught, we're dividing that by 1 over t. We're taking the mean there. And for a sub n and b sub n, we're multiplying that result by 2 over capital T. We can think of the definition of the Fourier transform in a similar fashion. I'm also going to have coefficients describing amplitude and phase at different frequencies, but now I no longer have a fundamental frequency to keep track of. And this is a result of allowing my period to be infinite for this aperiodic signal. So let's define that coefficient. And here I'm going to write this as a capital version of the time signal. So instead of little y of t, here I have capital Y of f. So in terms of notation, lowercase y, that's going to be a function of time. Capital Y, that'll be a function of frequency. So y of f here will be the integral from minus infinity to plus infinity of y of t times this complex exponential. And it's complex because I have this j term. J is the square root of -1. So what this is giving me is one complex coefficient at each frequency, as opposed to two coefficients at each frequency for the Fourier series. Now, I could think of this as two complex frequencies, ya of f and yb of f. And these would be defined in a similar fashion to what we saw in the Fourier series. So my ya coefficients, I'd be multiplying by a cosine term, and my yb coefficients, I'd be multiplying by a sine term. So in a sense, it's effectively the same thing. The benefit here is that using my capital Y of f, I can be responsible for, I can track simply one coefficient instead of two coefficients, a and b. And this is a direct result of using this complex exponential. So note here, this is a continuous function of frequency. If I want to determine my coefficient at a particular frequency, say f equals 2 hertz, I simply plug 2 hertz into this complex exponential for my frequency f here and solve. So really what the Fourier transform is allowing us to do is to go between these domains of time and frequency. So any function of time that we're used to working with, any lowercase y of t, by using the Fourier transform, I could transform that signal into a function of frequency. And the frequency domain is where we're going to be doing most of the manipulation of these signals. So for example, maybe you want to clean up a signal that we're reading from a particular sensor. Well, we're going to perform that operation in the frequency domain. And then once we're finished with that operation, we can always bring that signal back into the time domain using the inverse Fourier transform. The inverse Fourier transform is defined in a very similar fashion. Now we're computing our lowercase y of t, our continuous function in the time domain, and this will be a function of my coefficients capital Y of f in the frequency domain. And you'll notice once again, we're multiplying by a complex exponential, and we're taking our integral from minus infinity to infinity. And you'll note here, there's no minus sign in my complex exponential. So that's going to allow me to get from this frequency domain back to this time domain. So here's a quick example of this idea. Here is my recording from earlier saying, let's go terps. And you'll notice this is in the time domain. This is basically samples. So you could think of this, given some sampling rate, you could think of this axis as a time axis. I then applied a Fourier transform on this data and plotted the results here at right. And you'll notice that my voice was, primarily at lower frequencies, roughly say 5 to 700 hertz. And you'll notice there is what appears to be perhaps some noise that made its way through the microphone and was digitized. So here in the frequency domain, I could do some filtering, maybe remove the effects of those noise components. And then using my inverse Laplace transform, I could bring it back into the time domain.